My name is Tsebe. I'm the head of technology demonstration in the pyrometallurgy department at MINTEK in South Africa. I'll be taking you through just two of the pilot test work that we've done under the HAlMan project. And those two involve pre-reduction using hydrogen and then smelting using aluminium. Okay. All right, so the content of my presentation, like I said, the two sections that I'll be looking at is the pilot hydrogen pre-reduction of lumpy ore, and I'm looking at all these different sections here, and then also going to the pilot smelting of pre-reduced ore, as well as pilot smelting of high carbon ferromanganese slag. And I'll take you through the facility overview and the results that we've obtained, and also share then in closing future work that we're still going to do in this project. So MINTEK is a partner that participated with regards to pilot scale test work in work package 4, but we also participated in work package 3 for the small scale pilot test work. But for the purpose of the current discussion or presentation, I'll be just focusing on the pilot test work. So the two work that we've done, we're using the vertical retort. And the first trials were done in June 2024, where we prepared material to smelt in the campaign 1, which was completed in July 2024. Right, now looking into the pilot hydrogen pre-reduction work. Okay, so for the pre-reduction work, we used our, I think we call it a 200 kg capacity vertical retort furnace. This furnace, actually, the gas injection, we use gas cylinders where the flow rate is controlled using rotameters, and the gas is injected via a injection port located at the bottom of the tube. We also insert several thermocouples to monitor the temperature or profiling of the temperature inside the retort at different heights. And this is the actual picture that shows the vertical retort. And as you can see at the bottom there, that is the bottom pot that we use to inject the gases, which is also it's installed with a distribution plenum so that you have good distribution of the gases through your bed. Looking at the profiling of this vertical retort, as you can see, we had thermocouples inserted at different heights throughout the height of the retort. The first profiling that we tried to do, we could see that the first two or the top two thermocouples, they actually quite reached the temperature very quickly. And I think for this particular profiling, we had like 100 kgs of material filling the retort, which I think it went up to here. So these two thermocouples were not embedded into the material. So you can see there was a significant lag between the thermocouples, the thermocouple that was embedded in the material. So I think the material was 100 kg, it went up to here. And the three temperatures that were not embedded in the thermocouple, you could see they were all aligned, and they were showing similar temperatures. But the one thermocouple that was embedded in material, because we used only 100 kg, so it came up to there, it had a significant lag. So what we did is to improve this lag in temperature, we increased the amount of material in the retort so that we can cover the first two temperatures, and then these ones were exposed in the air, in the atmosphere, in the retort. But what we did to ensure that we minimize the lag is that we made sure that we overshoot the furnace temperature so that these can catch up quickly. And then that seemed to work, because our target temperature was around 700 to 750 degrees Celsius. And that seemed to work. And after we've profiled, we were happy that we continued with the first hydrogen pre-reduction tests. But before we did that, we also had to make sure that it is safe to operate with hydrogen. And one way of doing that, we actually just slowly increased the percentage or the ratio of hydrogen to argon. And we used a pilot flame to ensure that any unreacted hydrogen get combusted fully. Okay. So, and then we allow it to run for some time, and then also increase it to a more hydrogen ratio until we were running at 100% hydrogen. And as you can see, the flame was more intense and larger because there was more hydrogen coming through at the exit the exhaust gas of the retort. But yeah, so we were able to actually combust it fully. So we established that it is safe to operate with hydrogen. Then we went on to then use 200 kg batches for. So we completed 2 tests for the pre-reduction test using 20 millimeter top size manganese ore lumps. And the target temperature was 700 degrees Celsius. We're using, during heating up, we purge the retort with 10 liters per minute of argon. And then once we reach the temperature, only then do we introduce hydrogen and flowing it at 150 liters per minute. And we held the temperature for 4 hours. There you can see the flame roaring during the hydrogen reaction. At the end of the test, we actually then use the sampling spoon, which has 3 openings at different heights, to actually sample to different heights through the burden. Right. Okay. So, like I said, we only did 2 tests. So in the first trial, we didn't take temperatures at 3 points because the material was discharged before that could be done. So what we did is we just took a representative sample, grab samples to just do a quick analysis. Also, just to mention here that, sorry, this manganese is just expressed in manganese oxide. So this is not actually the manganese oxide, MNO. Okay, it's just expressed for simplicity. Then you can see in trial 2, we actually managed to get quite a number of samples to show the variations at the different heights. Okay, so because of the different temperature profiles, you do get different kinetics of reductions happening at the different height of your material in your retort. And what we've done now is we then took these 2 samples, which is the mid-center samples and the bottom center samples, and then put them through XRD to show. So the results showed that, let's say the mid-height center samples, that most of the manganese was actually pre-reduced from the bronite, the high manganese oxide phase, to the Mn2O3. Okay, so we can see that there is no MNO that was detected, meaning that the hydrogen reaction, sort of the hydrogen reduction, was not that efficient. Okay, and even more so for the bottom sample, where the temperature was also lagging a bit, we could see that bronite was still a major phase that was detected, and then there was some of the Mn2O3 was also detected as a major phase, but there is still no MNO that was detected to show that the hydrogen reduction as well was not, or pre-reduction didn't progress efficiently or to a great extent where you start forming the MNO phase. And the reasonable explanation for this is that the time that we allowed for the pre-reduction was not adequate to ensure that all these oxides are actually converted to MNO. And this was also actually, this work confirmed or validated the preliminary work that was done with the modeling work by one of the partners in the consortium. So the next work to actually improve the pre-reduction so that we have almost 99% of the manganese oxides pre-reduced to MNO is to actually then just extend the residence time. So we're looking at 6 hours instead of 4 hours, or even up to 8 hours. Okay. Now moving on to the, so for this work in the pellet, so we basically did 2 trials, and we think we generated about 300 kgs, which we decided to use during the pellet smelting campaign, but only as a transition, because as you will see later on in the slides. So for the pellet smelting part of the work, we're looking at 2 scenarios where we smelted the high carbon ferromanganese slag, so that we can demonstrate the HAlMan process, and that it is also capable of processing secondary manganese resources. And we also did pellet smelting of pre-reduced ore, which is then for production from primary resources. So before we did the pellet smelt testing, we do the preliminary simulation based on work that was done at the lab scale. So the recipes that we used here were based on the work that was done at lab scale test work. So as you can see here, we have the composition of the high carbon ferromanganese, and then this amount of aluminium was was based on the recipe mass that was used to get the highest reduction from crucible scale test work. And one thing here, you'll see that this high carbon ferromanganese slag has high concentration of silica and a relatively low concentration of MnO. Okay, so for this particular situation, we were targeting an alumina content of about 20% in the slag, with about 3% MnO in the slag, and then we're aiming to get like 75% manganese in the alloy. And also one other aspect or parameter to remember is the estimated specific energy requirement per ton of feed, okay, at about 0.5. So that is scenario 1. So this is smelting of secondary manganese resource. Scenario 2, we looked at smelting of pre-reduced lumpy ore. And in this case, like I said, for MINTEK, we only generated 300 kgs, and actually the pre-reduction didn't progress to far enough. So what we did for this work, we actually used pre-reduced lumpy ore that was smelted at Sintef by Caspar, as he explained. So they managed to ship it to us, and then the composition that you see here is the composition from the work that Caspar did at Sintef. So you will notice now that the manganese oxide in this material is much higher than the slag, and the silicon content is much lower. So for this particular system, we're aiming to achieve about close to 50% alumina in the slag, and we're hoping to achieve 82% manganese in the slag. And you can see for pre-reduced ore, the specific energy requirement is predicted to be much lower than when you're smelting slag. Right, so what facility did we use? We used MINTEK's 200 kilowatt DC furnace facility, which is remotely controlled and well facilitated with a feed system that is remotely controlled, as well as a circular furnace with a central graphite electrode, as well as a dedicated off-gas handling system. And this is just pictures to show you the actual facility. And as you can see, the furnace was refractory lined with, I think, 96% MgO bricks. Okay, this is the picture of the fully assembled set. So we used a bi-level tap holes for tapping slag and metal. Right, this is just the overview of the actual experimental plan that was executed. Just to bring your focus, so the first 20 taps were smelting the high carbon ferromanganese slag. And as you can see, the first condition, we just basically doing thermal and chemical stabilization. And then further adjustments were done to the SER so that we can get our target temperatures. But we also had to adjust to the aluminium addition. Remember, we said the initial aluminium addition was based on lab scale test work, but we realized that there is efficiency issues when you move up in scale, and that's the reason why pilot scale test work need to be done to validate the process efficiencies with any smelting operation. So to get to those target, the targeted like 3% MnO in the slag, we actually had to increase aluminum all the way from 9% to 11% addition. Okay. Then the other conditions, or the second scenario of the test work, as you can see here, only 3 batches or 3 taps we used MINTEK pre-reduced ore as a transition before we can use the thoroughly pre-reduced ore from Sintef. And here, remember I showed you for the pre-reduced ore, the manganese content was much higher. And as you can see, to also get the target low manganese in the slag, we had to increase the theoretical aluminium addition from 26 all the way to 32 before we can even get meaningful or close to the target MnO in the slag. Right, so the campaign was run over a period of 4 days. We had like 32 slag tabs and 11 metal tabs, and we managed to produce like a ton of metal and 4 tons of slag. This just shows the current and voltage set points. So you can see that there was very good control of the voltage during the test work. So the set point for current. So what we're showing is on the markers, this shows the average current. So the reason why it looks like we were off target or off the set point is purely because this is a current, it's an average current calculation. And remember, during every tab, we bring down the current, and then we switch off sometimes to do to do sounding or bath inspections. And then when it averages out, then it becomes lower than the current set point, which means it might appear as though we were not operating at the set point, but that is not the case. Okay, a similar phenomenon is observed with power input. Okay, so that is the set point, but it seems like the markers are not on the line, and the same scenario or same explanation is given for current applies for here, because current power is voltage times current. Okay. Now, yeah. So for the slag smelting section, tap 1 to 20, our target temperatures were like 15 to 1600 degrees Celsius, and as you can see, we were close to our target temperatures. And for the pre-reduced smelting of pre-reduced, our target temperatures were above 1600 to 1650. So as you can see, we are also close. We are very high there. And that's why we had to adjust the SCR a bit so that we don't superheat the slag metal. Right. These are the so from the actual test work. Remember the preliminary simulation gives you an indication of your SCR based on the conditions that you input. But during the test work, you can then also do a calculation or measurement of your SCR. So the SCR is given by the coefficient of X in this linear equation. And as you can see, for smelting of a slag, the SCR is 0.6. The preliminary simulation estimated 0.5. And obviously the reason for this difference is because we had to add much more aluminium than what was initially simulated. A similar thing with the pre-reduced ore. So the actual measurements during the test work gave us an SCR of 0.4, while the simulation gave us a estimated 0.2. And still, again, here it was because the simulation estimated that we're going to need much less aluminium, but at pallet scale, at a larger scale, the efficiencies are not so great. So we had to add much more aluminium, obviously, then meaning that more energy will be required. Great. Now, I'll just give you the chemical composition of the alloy that we tapped during the campaign. So remember, from tap 1 to tap 20, this was during the time when we were smelting slag. And the one other thing that you'll notice, the manganese was increasing with every tap. It's because we started off with an alloy as the starting metal heel that didn't have a high alloy content, high manganese content. And that basically distorted this initial manganese concentration. But at the end of the batch, we also managed to get like 70%. Our target was to get like 75%. So when we transitioned to the pre-reduction, as you can see, the iron was actually getting diluted because there was more and more manganese introduced into the alloy. When we transitioned to the pre-reduction, or at least you can see now that we didn't go through the same issue here, because we started off with the alloy in the heel that had high manganese. And as you can see now, this manganese also, it was quick to actually go up to, I think, 70 to 75%. But for this particular scenario, we're actually aiming to get like 80%. So what happened? We can look at the impurities. So with every with increasing aluminum addition, we also saw that you also introduce more silicon into your alloy. Okay. And that's why we're seeing also aluminum also diluting the grade of the manganese. And you can see that clear distinction when you transition to pre-reduced ore, that your impurities and your system, or alloy system, changes completely, and that now silicon is no longer that much of a problem in terms of as an impurity. But because we had to add much more aluminium to get to that lower manganese, you can start to see the silicon actually coming up as an impurity as well. Now, in terms of the slags, as you can see, we progressively, so this is the MNO, we progressively had to increase the aluminium so that we can reach that target below 4% MNO. And when we transitioned to the pre-reduced ore, you can see the manganese, because of the high manganese oxide in the pre-reduced ore, the residual manganese oxide in the slag was quite high. That's why we had to significantly increase the aluminum addition so that we can drop it significantly to the target MNO in the slag. What about the other slag forming, major slag forming components? They were relatively consistent throughout the test work. So you can see MgO there. It's quite consistent throughout, as well as lime. It's quite consistent throughout. But when you start feeding, when you start smelting the pre-reduced ore, you'll see that there was a jump here because the more aluminium reductant we add, we had to also increase the lime so that we can flux the alumina that goes into the slag. And that's why we see this jump here. Okay. Right, so future plans is for us to basically characterize and pre-reduce at 3.5 tons of UMK and ensuring all lumps so that we can use it in the second campaign. We're also expecting the 1.5 tons of fines, pre-reduced fines from Calix from Australia. We'll then do the detailed characterization of the pre-reduced ore, just to also confirm that we've pre-reduced most of the manganese to MNO. Then also determine the pre-reduction kinetics, and then we've actually started placing orders for long lead items like refractory dry rammables and spider plates and so on, and start preparing the facility for the next campaign. So the next campaign we'll be looking at scenario 3, which is smelting of pre-reduced fines. Okay, so what we've done there in campaign 1 was pre-reduced lumpy ore. Okay, so we also want to demonstrate pre-reduced fines, and we can do that because in this particular phase we are demonstrating the HAlMan using a DC arc furnace. Okay, so we are busy actually preparing the facility, and we will then also fine-tune the model so that we can improve the prediction of scenario 3 process flow sheet. We will also be smelting UMK as well as enchantering ore just to generate additional information from this campaign, because we can't just run a 1.5 campaign. So it's an opportunity for us to repeat enchantering ore as well as introduce another ore into this study, so that we can have much more information at the pallet scale, and then also then run that. Thank you very much.